New from where we left off, property relation for isentropic flow of ideal gases. We're going to see how some properties are related for this type of flow. Okay, first let's develop the relations between the static properties and the stagnation properties. Okay, reminder, static properties are normally not denoted by any subscript or maybe 1, 2, 3 to show that they are corresponding to a certain point in the flow. For example, T or T1, T2, T3 and so on. Stagnation properties are written like this. Okay, so we're going to develop a link between them for ideal gases in terms of the specific heat ratio K and the Mach number. So actually we have done this before, but not in terms of K and Mach number. Okay, we assume the flow is isentropic, of course, and that the gas has constant specific heat. So the temperature of an ideal gas anywhere in the flow is related to the stagnation temperature. So we've seen this equation before. So this is stagnation temperature in terms of static temperature, and then we have velocity of the flow and the specific heat of the gas. Okay, or if you rearrange, you get this. Divide by T, we get this version of the equation. Now, note that we can get Cp equals to Kr over K minus 1. Okay, this is 1. And then C squared is KRT. Okay, this was from the previous week's topic. Okay, and Mach number is V over C. So what happens when you combine these three into this equation? We get this. Okay, and you can simplify, and this will be the version that we can use. So it is still describing T naught over T, the same thing, but this one is in terms of K, which is the specific heat ratio, and the Mach number. So we don't need the value of velocity Cp to get this version. Okay, so that is for the temperature relation between stagnation temperature and static temperature. We can also do the same for pressure, okay, and density. So we have pressure relation or pressure ratio and the density ratio. So these three new equations are developed from what you have already learned from the previous week's topic. Okay, so now let's talk about critical properties. So we have those three new equations, right? Critical properties are properties of a fluid at the throat, where Mach number is unity. Remember, Mach number is unity, means Mach equals to 1. In the converging diverging nozzle, this is where the area is smallest. Okay, if you recall from previous video. So what happens at the throat will give you the critical properties. Whatever properties are there, they are called the critical properties. So ratios that we have developed in the previous slide are called critical ratios. Okay, just now we saw the stagnation temperature ratio, stagnation pressure ratio, and the density ratio. So these are actually called critical ratios. Okay, we develop them first and then we name them. So setting the Mach number equals to 1, okay, the critical point. If we set this into the equation 18, 19, and 20, we get this because Mach equals to 1. Okay, you can pause and look back at the previous slide if you wish to. You can see for yourself how we get these equations. Okay, so when Mach equals to 1, it happens at the throat of the nozzle, the properties become critical properties. Okay, and the T becomes T with a asterisk here to show that this is a critical temperature, critical pressure, critical density. Okay, do bear in mind, however, that these critical properties, okay, the TP density, should not be confused with the thermodynamic properties of substances at the critical point. Critical point, if you recall, let's say we have the TV diagram. This is at the point where it's not clear whether the phases of the substance is interchangeable. It's not clearly defined, unlike under the bell, if you still remember. Okay, that's just the critical point. Yes, we call it critical temperature, critical pressure, but they're not the same as this. This is related to compressible flows. Okay, let's go through this example to find critical temperature and pressure in a gas flow. So calculate the critical pressure and temperature of CO2 for the flow conditions described in example 1. So in the previous example, we had this converging diverging nozzle at this inlet temperature. So we've established that these are the stagnation pressure and stagnation temperature of the flow. Okay, if you have to find the critical pressure, that means the pressure at the throat of the nozzle. Okay, so these are some assumptions. The flow is steady, adiabatic, no heat transfer, one-dimensional, and of course that the constant specific heat assumption is applied. We have the specific heat ratio. We're going to need the value of K, so we have had this from before. Okay, or you can look at table A2. So to determine, we just simply bring our equations. Right? Why are we using the version without Mach number? Because it is at Mach equals to 1. Okay, so it will result in 1. So it will not change the equations. So okay, putting in the values. We have value of K. Just simply substitute and you get the ratio for temperature is this. The ratio for pressure is this. But what we have to find are the critical pressure and critical temperature. These are the ratios. Okay, so to find this T star, you have to actually have the value of T naught. Do we have it? Yes. Pressure? Yes. So put that in. The critical temperature is what you got here, 0.87337 times stagnation temperature, 473, as established in the previous example. Okay, and critical pressure, also same thing, you get 767 kPa. Remember this from the previous video? It is the pressure corresponding with this point in the throat with the smallest area, 767 kPa. It started at 1400, ends at 200 kPa. Okay, so this is where we get the value. Okay, so that's it for this topic. In the next video, we're going to go through a few practice questions. I'm going to leave you with more questions for you to try.